Hello everyone. Welcome to our extra discussion session for the Physics of Nanoscale Devices NPTEL course. As always, I'm Jyoteshwaran, a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. So, in this session, what we shall attempt to do is have, just like what was done in the very last lecture of the course, what I shall be attempting to do is give a course summary. But rather than covering all the topics that was covered in the course, which would be impossible to be done in a 2 hour video, what I shall do is I shall focus on certain key topics with respect to their relevance in problems. So, and before I elaborate any further, I would like to emphasize and state for the record that this is my personal opinion. Like, I have never attended the NPTEL version of this course. I have attended this course as a part of my PhD coursework when it was taught in IIT Roorkee. So my only experience as far as learning the course goes comes from that. And I actually don't have an idea as to what questions are going to show up. But based on the course itself and my familiarity with the instructor of the course, I can tell that questions are by and large going to be focused on these areas. So the areas are as follows. We have the basics, which includes quantum mechanics and the Kronig-Penney model, and then we have the various expressions for density of states. We talk about Fermi distribution and statistics. Then we have the Landauer theory of transport, which is the ballistic transport. So this is equivalent to ballistic transport. So this is the ballistic transport model. And then we have we may have questions based on MOSFET characteristic, both classical and ballistic cases, and MOSFET electrostatics, and then we will also have uh, a brief discussion about double gate devices and strain engineering, and quantum dot devices, and finally end the discussion with thermoelectric effects. So there are 10 topics here, and the aim, like even before I begin, most of the questions by and large you can expect them to be more conceptual than numerical, because the aim of this course has always been to give a feel for the idea of nanoscale devices, like what is the need for them, and what are the underlying principles, and what are the potential benefits we gain from using uh, short channel or very short channel devices. So the fundamental aim of this course has always been understanding the concepts over solving numerical problems. Although there will be numerical problems, but you can expect the questions to be by and large conceptual. So if you understand the underlying theory and the concepts, you will have a relatively good time in the examinations. So without further delay, I shall start going through these topics one by one. So the first one, we have the basics of quantum mechanics and the Kronig-Penney model. So in this, what we should remember essentially is, so when we talk about this thing, let me just get rid of this. Yeah. So the primary thing to remember is, of course, the Schrodinger's equation. So, and the version that we shall be using is the time independent form, where we just write h times psi of x, if you're talking about the wave function, is equal to e psi of x, where h is, and the problems that we are discussing in this course are mostly 1D problems. So this is the form, like by and large 1D. I mean, not by and large, almost exclusively 1D. you can rest assured that nobody is going to ask you to solve the two-dimensional Schrodinger's equation. So that is it. In this form, you may be given problems where you might have to solve the Schrodinger's equation like this. And we already have examples where we have a particle in a box, which is the only example that was explicitly solved in the lectures. So when we talk about particle in a box, we know En is equal to where I'm just using the generalized notation of the effective mass, and this is so the essential setup of the problem is given as such. We have v equal to infinity here, v equal to 0, and v equal to infinity. And we are also assuming that this point is x equal to 0. So in that case, we will have the functions as sine waves. And so this is for x lying between 0 to L, and psi of x is 0 otherwise. And so these are the formulae, and the concepts that have to be remembered over here are whenever we introduce confinement into a system. So confinement will lead to quantization. So that is the very first thing, which is a concept that will be invoked again and again and again in this course. So always remember this: wherever there is confinement, there is going to be quantization. Wherever we see quantization, we should expect some form of confinement to have occurred in that system. And outside of this, all wave function solutions and other things depend on boundary conditions. So I'm not going to spend like too much detail in this because, in my opinion, this will not constitute a very great, part of your, in terms of mark weightage. So remember the boundary conditions. If you don't remember them, you can go to the week 1 session, or you can look at the corresponding lectures and understand what are the properties of a wave function that need to be obeyed. So I'll just briefly write them here. So we would like to have continuity. Continuity, and then under special circumstances, the derivative is also expected to be continuous. And of course, the wave function is single valued; it cannot have multiple values at any given point. And we will also expect the wave function to be normalized, like integral over the entire space. The value of the mod squared of this wave function has to be 1. So that is essentially uh, to ensure that this thing also serves as a probability amplitude. So this is as far as quantum mechanics goes. This is what is there. And then after this, the other basic topic that we looked at is the Kronig-Penney model. So in the Kronig-Penney model, don't have to worry too much about the derivation. Like, it's highly unlikely that those things will show up as questions. However, the most important thing, again, in my opinion, is the transcendental equation that we get at the end of the uh, derivation. So we have the transcendental equation, which, again, I'm not writing the equation, so you will have a waveform that goes essentially like, not a waveform, a graph that goes like this. So this thing will like keep oscillating. And let us say I have +1 and let me make it slightly lower also. So let me say I have +1 and -1 at these points. So this kind of defines the allowed energy values. So we have the transcendental function, which is, let me say it is some, yeah, f of xi, and we have xi over here. So this will kind of tell us where the various energy bands lie. Okay, yeah, I made this thing too low. So, you know what? Since this is the last time I shall be doing this, I'll just take a little bit of extra time and try to draw this figure as correctly as possible. So, yeah. So I'll make yes, so that I have at least 3 bands in the system. So we just take these values. So this will cut over here also. So these regions where this function kind of cuts with this will give us the allowed energy levels. So from here through all the way till here. So this is going to be the second set of, yeah, allowed bands, and then we are going to have from here to here. So this is the third set of allowed energy levels, and then we have the fourth set and the fifth, so on and so forth. So these are our energy bands, and what should be remembered here is, and of course these regions constitute the energy bands. Although in this figure I have not represented that quite correctly. So these are the allowed energy bands. Or no, it has come out more or less correctly. So let me just use a different color here. So the blue lines tell us what the allowed energy levels are. The gaps are the forbidden energy levels, which form the band gap. What is to be noted is that as we go up the band hierarchy, the bands become broader and broader. So as energy increases, bands become broader. Broader, and band gaps become narrower. And the associated K values with these constitute the Brillouin zones. Also worth remembering is the reduced zone representation, where we will essentially represent the complete band structure as such. So we will have the second band, which will have more, like essentially the energy values that will come into it will always be more than the first band. Oh no, I do the second and first. Sorry. So yeah. So the first one is going to be here. Yeah. It's going to be like this. And then we're going to have the second one, which will be slightly higher than that. And third one still higher, so on. And in the reduced zone, we just represent this whole thing from minus pi by a to 0 to pi by a, where a is the fundamental, so a is the period of the lattice. Like in the lectures, you might see this as A plus B, where A is the region where the potential is non-zero and B is the region where it is zero. I'm just writing A plus B as some new variable A. Okay, and of course these the minima will coincide. Like it will never be the case where the minimas and maximas don't coincide. So what needs to be remembered is that the concept of HOMO and LUMO. So this is the highest occupied MO, molecular orbital. And we have LUMO, which is lowest unoccupied. And this is typically considered to be a conduction band. This is typically considered to be the valence band. And of course, there is the band gap. So, and remember that the band gap is always calculated from the, I will leave it as it is, from the minima of the two bands. So over here, you should not erroneously calculate, if you are asked to calculate the band gaps, you should not calculate it between this point and this point. Like this separation here, I mean, although it is obvious, I'm just telling this so that nobody makes this mistake. This is not EG. Okay, so EG is measured over here between these two bands. So this is EG. Okay, so this is the correct one, and this is the wrong band gap. Whereas here, the maxima and minima are aligned over this point. So you should take the maxima of the lower band and the minima of the upper band. So that is how it will always be. So the highest level of the highest energy level of the lower band minus the lowest energy level of the upper band. So this is the highest point, this is the lowest point. So the difference between that will always be the band gap in the KP model. So these are the things that you have to remember, these definitions. So using that, you should be able to guess, I will not guess, answer most if not all the questions that occur in this topic. So with this, we are done with the first module of the course. So just drop this down, far down. Yeah. So second topic that we shall look at is the density of states. So density of states is actually fairly straightforward. Not going to spend any time doing the derivations. All we have to remember, I mean the most important things to remember are these proportionality relations. So G2D proportional to e to the power 0, which is a constant, and G3D is proportional to e to the power half. So again, questions are going to be multiple choice. So almost invariably, you are going to end up with these things. Alternatively, you might be given a graphical representation. So 1 over square root of E is going to look something like this. So this is E and this is G of E. So similarly, this thing over here, you'll have a constant. Now, I should make a concerted effort to do that. Although we derive these functions, typically in realistic problems, we shall be talking about density of states in the conduction band or the valence band. So usually we have a limiting energy, so that is either EC or some band edge. So typically it is the lowest energy of the conduction band. And so similarly over here also we will have some starting point, and after that the density of states will be constant. Below that it's going to be considered to be zero. So this is again g of e. So this is 1D case, this is the 2D case, and this is the 3D case. So again, this will be some EC. So these are the things that you will have to remember by and large. And I mean, it may also help you to remember the exact expressions. The most important one that you will have to remember is G2D, which is m star upon pi h bar square. So this is something you'll have to remember for multiple reasons, which I shall come to. The other two also you can go ahead and look them up. They are easy enough expressions. So just remember what they are, and most of your questions regarding density of states, like by most I mean like any possible question, one or two that shows up is going to be more or less pertaining to this. So density of states, like mercifully, is over rather briefly. So I'll slide this down one more level. Fermi distribution, again, likewise, it's going to be a brief topic, but the reason why I'm talking about them separately is that these two will have far-reaching consequences in the rest of the course, as you will see. So most important thing to remember here is the function itself minus EF by KBT, and important property is f of EF is equal to half no matter what the temperature, and at T equal to 0 Kelvin, Fermi distribution function is going to look something like this. This should be a solid line. So it is going to be, up until this point, it's going to be whatever the Fermi level is, and at EF, it will suddenly drop to 0. So this is the E axis, and this is f of E. And for any higher temperature, it's going to be I'm sorry. But luckily, people won't have to put up with this anymore after this week. So, yeah. Yes. So, this is at higher temperatures, and this is always going to be, God, this is always going to be half, although this figure is not very representative of that fact. This is 1 and this is 0. So, at like lower energy levels, for me, function will always have a value 1. As it increases for finite temperatures, it will start going below 1, and at Fermi level, it is always going to be half. So that is directly from the property of the uh, Fermi function. Another thing to be remembered: this drop over here and this over here. So this is always going to be symmetric about this. So essentially, f of E is equal to 1 minus f of E minus EF. Am I writing this correctly? Or should it be minus EF and E plus EF? should be E minus EF and E plus EF. So essentially f of E minus EF is equal to 1 minus f of E plus EF. So setting E equal to 0 will give you 2 f of EF is equal to 1, which gives us this. So this will always be followed. So you may have some numerical questions where this rule needs to be applied. This was like explicitly when derived in one of the discussion sessions, so you can go back and look at that. And what else is important in this? So outside of this, we have, I'm just making sure I'm not missing anything. And this is the blue line is at t greater than 0k. Yes, of course. So just for the sake of completion, so this is F Fermi-Dirac, Fd. Other than this, we also have the distribution function for Bose-Einstein, which is 1 divided by 1 plus e to the power E plus EF upon kBt. And then we also have Maxwell-Boltzmann, where there is no particular notion of like Fermi levels, so or chemical potentials. So we just write it as E by kBt. So and like typically this would be like E minus EC or something that is from zero energy reference, but the notion of Fermi energy where we have like definite values is no longer applicable here. And oh no, wait, I'm sorry, it's not like this, it is minus here and still minus up there. So, apologies for that. So this function kind of like diverges at the Fermi level. So again, you might be asked to remember these things. So for reference, I'm placing it here. So the reason I'm writing all these things is that like before your exam, you can just go through these slides and have a quick refresh of the topics. So there is that. And what else do we have in Fermi distribution? Yeah, for now, and of course, not to be missed, integral. So typically we write this as 0 to infinity, but so f of e dE is equal to 1. Sometimes we may also choose to write it as minus infinity to infinity. It should just be understood that the zero energy reference level is pushed all the way to minus infinity. So this doesn't mean that we have like negative values of energy. It is just a reference shift. So this is also equal to 1. So depending on the context, we might either write it as this or like this, or we might also choose to write it as some EC to infinity also. Okay, so always keep that in mind. So Fermi distribution function is also done in one slide. Yes, now we come to, in my opinion, the most important part of this course. By no means am I implying that this will be the most, the most tested part of the course. But if you remember the things that are going to be discussed here well, much of the later part of the course will become that much more easier to understand and reason out. If you remember this, like on the fly during the examination, you want to be able to answer the questions more or less easily. So when we are talking about the Landauer theory of transport, things that need to be remembered. Stored charge is given by 2q upon h. Integral, we have of E times so when I again for the last time, so when I'm talking about two terminal devices, we have a source and a drain which are treated as bulk. Always remember this. And I have a channel. So I will call this electrode 1. I'm not distinguishing between source and drain here because this device, for all intents and purposes, will show symmetric behavior. So, and then we have the channel. So, yeah, yes, divided by 2 dE. So this gives us the uh, charge that is stored in the so here again the limits I'm not giving, so the limits are the relevant values of the limits. Will that be 2q by h? Should that be a 2, like more important question is should that be a 2q by h? uh, just 1 second, I'm sorry for this, like, oversight. Let me just quickly refresh it. I just want to make sure that I'm not making any mistakes on this. So yeah, apologies for that like interruption. There will be no factor there, of course. So this is like in this quantity is just the number of charge, like number of charged particles. So here I'll just mention this. So this will just give us the number of electrons. So this multiplied by the charge of the electron will be the total charge that is stored in the channel. Okay, and the current is integral. So here we will have the factor of 2q upon h. So we will have d of e times gamma of e, which is the energy broadening. So and it's going to be pi times gamma of e. F2 minus F1 d of e. So yeah, and this quantity over here gives us the number of moles. So this is what we write as m of e, and gamma of e is h divided by tau of e, which is the transition time, or rather not transition time, the transit time. So what we have here is essentially a quantum mechanical expression. Over here it is fairly simple. Like we just find out the equilibrium condition. The Fermi distributions kind of give us the probability of electrons being present in electrode 1 and electrode 2. And we are just, this is essentially a probability summation. So we just find the probability of electrons existing in the channel, and that probability should give us an idea of the number of electrons we are going to find in the channel. Whereas here, that probability concept coupled with this thing over here, which is the transit time, which kind of gives us a notion of velocity. So this is something like velocity. This is not exactly a velocity because quantum mechanically the idea of velocity doesn't make much sense because I cannot, precisely state the position of a quantum particle. So this is something like velocity. So what we are doing here, and of course we will see that eventually we will write this as the velocity. So the thing that needs to be seen is quite simple. What we have here is the uh, number of modes, which depends on the available number of energy levels and the idea of energy broadening type to it, which gives us the essentially something like velocity. So Alternatively, what I can do is I can multiply d of e into f2 minus f1, which kind of gives me the probability of finding the electron, and this gives me the velocity, something like the velocity of the electron. So over here, this expression, what it essentially means is, I'm just looking at my channel, finding out the energy velocity of a particular electron with energy E, calculating the probability of finding that electron, multiplying the two, and then summing over all possible values of energy. So that is essentially what it is. So in that sense, this expression here is also a probability summation. Now, when we are including diffusive effects, so like when the channel length becomes longer and longer, this expression here will become T of E, M of E times F2 minus F1 D. So this is the most general expression that we shall be dealing with, and T of E is 1 plus, I'm sorry, it's not 1 plus, it is lambda divided by lambda plus alpha. Yes. So it is going to be this. This quantity is always going to be less than 1. Uh, and for very small L, where L is like very small compared to lambda, so T of E is approximately equal to 1. For L significantly less than lambda. Now, lambda, of course, is also a function of E, not to be missed. If you are not given any expression or any value for lambda of E, you can go ahead and assume. So, lambda of E is approximately equal to the de Broglie wavelength. So if you don't have any other choice, and if you are asked to evaluate this, just evaluate the de Broglie wavelength for the electron at that energy. So this is h by p, the momentum. So just evaluate this and substitute it over here. So that should give you an approximate value of the transmission coefficient. Okay, and for large L, T of E is approximately equal to lambda by L for L very much larger than lambda. So these are the two limits that we will consider. And so essentially what is happening is the effective number of modes is kind of reduced as the channel length increases and diffusive effects start to dominate. So those are the things that you have to remember. Concept wise, the first thing that needs to be remembered is even in the diffusive limit, in the Landauer model, no scattering occurs in channel. Okay, so no energy loss, therefore no energy loss can occur. Energy loss or gain, like no energy transference occurs in the channel. Okay, and second, energy loss occurs at the interface. And third, we will also we what is to be remembered here is that this is, I mean, I should have written this first. This is a semi-classical treatment where we also like no scattering occurs and no acceleration of the electron also. Even though an electric field is kind of, there is a potential difference and there is an electric field between, like if I have something like a input voltage V here, and if this thing is grounded, even though there exists an electric field, I will not assume that this electron here is being accelerated through the channel. So it's a semi-classical treatment. So this is not purely quantum mechanical. We have just included some quantum effects with some approximations. So it's a semi-classical treatment and no acceleration in the channel. So there is no scattering and there is also no, why am I misspelling things so much? Acceleration. Yes, in channel. So that is also not happening. So no energy loss and no energy gain also. Okay, and at the interface, so if I have if I know that the energy loss is E, then it occurs like a fraction half at each interface. So, so half at each interface. Again, I have to like this is even like outside of the course also. This is in no way reflective of what is actually happening in the channel because this whole process is quantum mechanical. We can never like peer into the channel and see what is happening. This is the model that we are proposing. So this does not reflect what is actually happening in the channel. So, as a general rule, you will have to remember that whatever models we are proposing, it is just a mathematical system that is supposed to give us some models with which we can predict the behavior of the system in reality. Okay. So, in channel. So, these are the conceptual things that need to be remembered. And then, yes, so we have this. Now we have some special conditions. So, we have special conditions. So what are the special conditions for this? So first we have low bias. So the very first one is the low bias case, in which case we come up with our Fermi window function. So f2 minus f1 is approximately equal to dou f upon dou e dv uh, minus dou f upon dou e dv, which is we have seen this. Oh no, dou EF which is equal to dou F upon dou E dV. So, of course, Q times dV. Q times dV. Huh? So, because this is like an energy differential, this thing has to be this has to be dE, which we shall write it as Q dV. And because of that, we get the current expression where we have 2Q squared upon H integral T of E, M of E, dou F upon dou E dE. So this function is the Fermi window function. And the graph looks, so this is EF, it is a function that is symmetric around EF. Like the explicit form, you can like perform the derivatives and find out. I would suggest that you do that at least once for practice. Due to the shortage of time, I'm not doing it here, but you can also refer to the previous sessions. So I'm sure I have also done the derivation at least or once before. So it's going to look something like this, and it's going to be symmetric. So this is EF, okay, and this thing is a dou F upon dou E. And if we are looking at, no, it's going to be the negative of this, yes, because the function's value like falls and then rises. Now at t equal to 0, dou F upon dou E is going to be minus, yes, the minus actually occurs here, is equal to minus delta E minus EF. So it becomes the Dirac delta function. Okay, and this is important. So this is the first special case. This directly leads to our second special case, which is B, low bias, low temperature. Okay, so at low bias, low temperature, the current is quite literally 2q squared upon h. Wait, have I done this correctly? Oh, yeah, of course I missed that, times V. So this is the applied voltage V. So this whole quantity is the conductance, and this is the quantum of conductance. So this quantity here, this is the quantum of conductance. So the reciprocal of this is approximately 13 kilo, like 12.8 kilo. So, serves well to remember. But again, you can, if required, you can calculate it on the spot also into Unu. Color mismatch is into T of EF, M of EF times V. So this is it. So in general, G at t equal to 0, K, and this is small voltage, small bias. T equal to 0 is also sometimes just called low temperature. So you can, if it is mentioned low temperature, you can assume things to be like, so here, yeah, I've written that already here, approximately 0 Kelvin also, you can go ahead and take this result. Okay, so there is that. So you have this, and what am I missing? Oh, I'm not missing anything. Okay, so G is going to be I by V, so that will give us 2q squared upon H into D of EF times M of EF. So typically, if we look at the short channels, even this will be approximately equal to 1 at most times. So for fully in the ballistic limit, this is going to be just this into this. Now, that brings us to the third special case, a 2D channel, where I know M of E is equal to number of half wavelengths that fit along the channel width. So you don't even have to do the calculation, the density of states calculation. And this is a very handy result which will help you solve a lot of numericals. So this is W by lambda de Broglie divided by T. So this gives you the a number of modes. So to calculate the number of modes at the Fermi level, just substitute the value of the um, at de Broglie wavelength at the Fermi level. And a related and important expression is this. So if you want to find out what kf is, then so this you will get from the fact that pi kf squared is going to be twice the number of electrons in a 2D system. So from that you will get this is equal to 2ns, which is the surface charge density, divided by pi whole power half. So this is for 2D systems. So where h squared, kf squared upon 2m star is equal to EF. So this will kind of allow you to find out the like if you know KF, then you can find out lambda dB directly. So usually you will be given this quantity and you will be asked to find the current that flows through. So this is the root for this. These are typically the numericals that I've seen be asked here. So there is this. So this is strictly for 2D systems. For 3D and 1D systems, I have done similar calculations. So I would recommend that you go back and look at that. Look at that if you feel it is necessary. Although this is more important than that. So there is this. Is there anything else I would like to emphasize more? No, probably not. Like later, I will look at things. Oh no, of course there is. I'm sorry, I overlooked it. Yes. So the final thing that we have to look at in this thing are the Fermi integrals. So before I begin the Fermi integrals, M of E is D of E like proportional to 1 over tau of E. Now the reason I said this is like velocity is that will automatically give us, so what I can tell directly is 1 over tau of E is always proportional to e to the power half. Okay, which is why I know m1d of E is now proportional to e to the power half because d of E is the density of states. So e to the power half m2d of E is proportional to, oh no, not e to the power half. Why did I do that? E to the power 0 because e to the power minus half into e to the power half. And this is going to be proportional to e to the power half and m3d of E is going to be proportional to E. Now, so yeah, even before I talk about Fermi integrals, these are mode. So mode. This is the mode distribution function. Distribution function. So now you can guess that this does not depend on it. Again, I have explicitly calculated the 1D conductance for a ballistic channel. That has been calculated, so it will come out to be something like 4 ohms. So you can go back and look at that derivation. Whichever week this idea of modes was covered, I solved that problem during that session. So M2D we know in terms of de Broglie wavelengths. M3D you can remember the exact expression if required. But what is important here is the following. this implies I is proportional to integral m of e times f of e dE. So this gives us the idea of Fermi integrals. So essentially, whatever power of E that occurs here, that will directly tell us the Fermi integral that is happening. So for a 1D channel, so from like here, like these are, in the form of Fermi integrals. So this is why we even discussed Fermi integrals to begin with. Okay, so for a 1D channel, the current I is going to be proportional to 1D, 2D, and 3D. So yeah, I can just say mode distribution slash Fermi integrals. So again, nobody will ask you to, I mean, more or less, I'm 90% sure that nobody is going to ask you to write the exact expression. But people will definitely ask you what kind of a Fermi distribution function, sorry, Fermi integral would you expect in a certain current expression or say charge expression. So for that, you will have to remember which terms appear in the integral, and that should give you the answer for what kind of a Fermi integral should appear. Okay, so is that? Yes. So I is proportional to, over here we will have Fermi order 0, so F0 of eta F. Over here I is proportional to F half of eta F, and I is proportional to F1 of eta F. So this is the order in which it goes. One more thing that needs to be remembered is dou by dou E of, or I mean, technically speaking, it is dou by dou eta F. But as we know, dou by dou EF and dou by dou E are related. So of F n eta F will always give us a constant. It's proportional to n minus 1. So it will go down one order when I take the partial derivative. So if this is true for the current, then if I'm told small bias is applied, remember that this will go to minus half. This will go to minus 1 and this will go to 0. Okay, so I will just write it here, which implies low bias current expression will have Fermi integral order of 1 less. So like I'll just also write it here. So this will be F minus 1 of eta F. So this is high bias and this is low bias. And again, since the integral itself is being evaluated, you will have to understand that all of this is happening at a finite temperature. Okay, because at zero temperature, this Fermi window function or whatever becomes like it is either a constant and then drops off to zero, or it is a Dirac delta function for low bias case. So there, an integral actually doesn't need to be performed. Okay, so we have f minus half. So remember what condition is given, like if we are talking about low bias, high bias, or what, and that will correspondingly allow you to identify which kind of a Fermi integral is appearing where. So this is for the current expression. Similarly, you can also look at the charge expression. I'm not writing that out here, but by now you should know what is what. Okay, so and this is more or less what is present in the Landauer model, which is why I said this is by far the most important in my opinion, because concept wise you have the most to remember here, and like new mathematical objects and artifacts are also introduced here. I've kind of summed up most of them, not most of them. I think this is pretty much everything. So, but nonetheless, I would also recommend everyone to go through these lectures once before the exam. So, because they have like a strong bearing on the rest of the course. So, yes. Yeah. Okay. So, moving on to our next topic. God, I've misspelled characteristics pretty badly. Yes. So, MOSFET characteristics. What we have to remember is no matter what kind of a MOSFET we have, I will want an output characteristic that looks like this. I will want a linear behavior and then some kind of a saturation. So this is VDS, this is IDS. So this is our output characteristic. And as opposed to the, not as opposed, and the corresponding transfer characteristic, here we are talking about VGS and IDS. So this is what we expect. Like again, I'm not talking about the theoretical I'm not talking about a theoretical transistor where this will be kind of like a straight line going flat, and this will be kind of a, again, it will be zero up to a certain point and then shoot up to infinity. I'm talking about a MOSFET. I'm talking about a real device. So this is what we will expect. So this is the transfer characteristic. So this is our expected things. So what needs to be remembered first and foremost, IDS is Cox times VGS minus VT. So this gives us the total uh, charge, or rather the charge density. Multiply that by the width to get the charge, and multiply this by VDS. In fact, this will be W by L. So this is going to give us the complete current that flows from. So typically, this thing will be given per unit area. So some of these things will also get cancelled out. Pay attention to what unit the offset capacitance is given as. On this note, yeah, there were a few questions asked like almost 2 weeks ago regarding. This is week 9 of the course. We have arrived at week 9 already. So there was an assignment question. You should have received the course notification that that particular question has undergone re-evaluation. So question 10, none of the options given were correct. So that will not be considered for evaluation. The error in the assignment is regretted, and rest assured nobody will get penalized for the error in that question. Okay, so a couple of the students, or rather, yeah, a couple of the students pointed that out, and we have kind of, you know, mitigated that error. Okay, so we have this, and this kind of like what should be understood most importantly is this entire device that we have. So we have a, I'll just quickly sketch that. So I have a source and a drain over here. I will have full on substrate and have an oxide layer, and on top of that there is a metal. So we have the source, we have the drain, and so yeah, I should have put drain and source the pattern. So this is source is typically considered to be grounded. Drain has a voltage VD. There is a gate voltage VG, and there is a substrate voltage also, which is the S of VGS. But as a general as a general rule, we can assume that this is also grounded. So this is so VGS is the same as this. Okay. So that is a convention that we follow almost like universally. So we have these two voltages that kind of control the current that is flowing through. The simple model for the classical MOSFET is that VG acts as a capacitor over here above a certain threshold voltage. So that again, this is strictly for VGS greater than VT. Please do not apply it for VGS less than VT and say a negative current is flowing. That will not happen. Beyond the threshold voltage, charge accumulation, or rather, I should say, charge inversion occurs in the substrate. So we have an inversion layer that is formed. Quick callback. This is a quantum confined layer, even in a classical MOSFET, and this provides the conduction channel. So the channel is kind of induced by this. Although the device is a bulk device, a uh, confined quasi 2D channel is formed over here. So yeah, at this point I remembered that I have not talked about subbands when I was talking about the Landauer model. Not to worry, I will talk about subbands when I go down to one of the later topics, like in a few more minutes. So yeah, so this is strictly for VGS greater than VT, and so yeah, we treat this as a capacitor. So the capacitor accumulates some charge, and a voltage is applied, and those charges kind of move from one electrode to the other. So that is the basic structure. And what else do we have over here? So we have, oh yes, of course, we have, um, yeah, I guess I will write that here as well. So we have ID SAT is 2L dash, which is the pinched off length of the channel, times the mobility of the electron, times the capacitance, into VGS minus VT whole square. So this is the ideal case. Okay, yeah, this is the ideal case saturation current. Although, in my opinion, too much time will not be spent on the like. As you have seen the assignment, also, not many questions were asked about this. This is the more important expression as far as the classical uh, MOSFET goes. Okay, so and that is pretty much everything that is required for the classical MOSFET. So just understanding this should more or less be enough. Yeah. Now when we are looking at the ballistic MOSFET, so when I'm looking at the ballistic MOSFET, again, what needs to be remembered are the various Fermi integrals. So this I have already, discussed in some detail in the Landauer model part. So just remember what the various Fermi integrals are. Most of the questions here are going to be conceptual, and you'll have to think about what the various dependencies are. So we are going to have like the various Fermi integrals, and then we shall be talking about the quantities Vx plus. So this is something that I should have discussed in the Landauer theory part, but I'm doing it here because it is more relevant here. And this quantity Vx, yeah. So this I should technically write it as at some energy E, and when there is a double averaging, we are also averaging over E. So these two quantities are important. So we will have to like, so this is this second, right? So this is 2 by pi V of E. Uh, yes, 2 by pi V of E, like there is nothing more. So this is 2 by pi V of E for a 2D system. And for a 3D system, it will just come out to be VE by 2. And for a 1D system, it will be VE. So this quantity again, like it will be this integrated over the energy values. So there will be a Fermi integral here, which implies this thing will also be a Fermi like a Fermi function, and therefore the resultant quantity will be a Fermi integral. Okay, and again remember that I is 2 cubed on h integral d of e m of e f2 minus f1. So this thing needs to be remembered always. So again, depending on your various channels and stuff, you will have different kind of Fermi integrals that give the current. In the saturation limit, also you will get a similar expression, although that is kind of, like, oh, I can tell that right here. So this is, these are like the first three things. And how does saturation occur in a ballistic MOSFET? This was discussed in the week 9 portion of our course. So in, or rather, this was discussed in week 10. In a ballistic MOSFET, saturation is a result of not channel pinch off, because no channel pinch off occurs in a ballistic channel. Yes, so I will write that here also. Okay, so I will write that saturation is caused by channel pinch off. So again, this is a like conceptual point that needs to be remembered over here. Saturation is a result of velocity saturation. Velocity saturation. Okay, so and the idea of velocity saturation is like there is only a finitely many number of electrons in my channel. So if I have some kind of a velocity distribution, ideally this will be a 2D distribution function. The point is, after a certain point, like as, so this is at say V equal to 0, where like this is the voltage. Now VDS, yeah, I'll write it like that. Now the point is, as VDS keeps increasing further and further and further, this side will become smaller and this side will become that much larger. So this is V. So this is Vx. So this is kind of what happens. Vx and this is Vds greater than 0, or rather much larger than 0. So eventually this thing will vanish and all the things will shift here and there will be no more electrons to actually move in the positive x direction. Because of that, we will have what is called velocity saturation, and velocity saturation in turn leads to current saturation. So these are the most important things that, so I will also point out here that these are Fermi integrals. So in general, calculation of Fermi integrals other than the order zero integral is non-trivial. So order zero integral has been calculated, so it will be a log of 1 plus eta f. So, or rather 1 plus exponential eta f. So that part uh, has been done in the slides. So you can just look up that expression. So this is the thing about ballistic MOSFETs. So yeah. Now when we talk about MOSFET electrostatics, first thing that needs to be remembered is inversion. So inversion occurs. So inversion occurs at an inversion potential. Potential. Just 1 minute. Yeah. So I'm back. So yes. So the inversion potential, which is given by psi inversion, is 2. It should be given by 2 kBT upon Q. Like, I mean, this has to have units of voltage. So kBT upon Q ensures that. So you can actually guess this expression without thinking much about it. Na by Ni. So ideally what I want is, in an NMOS, I want my P channel to become, not P channel, the P substrate in the channel region to act like an N material. So essentially, my intrinsic electrons, which is usually what is present, Na by Ni is the amount of electrons that are present. I will want all of that to kind of, I, I will want the situation to kind of flip over. I will want Na electrons to be present in the channel. So this will give us that particular value of the inversion potential. So this is what needs to be, this is the potential that needs to be applied to achieve inversion. However, we should remember that in this model of the MOS capacitance, there are at least 2 capacitance values. So we have Cox and then we have CD, the device capacitance. So this is the oxide layer capacitance. And this is the device capacitance or depletion capacitance. There are other capacitive effects also present, but we are considering only these two. Okay, so capacitance. Now, oh yes, before I talk about MOSFET electrostatics, I should have written this here. So going back to MOSFET characteristics, make sure to remember the definition of DIBL, drain induced barrier lowering, and subthreshold swing. So, and subthreshold swing should be around like, so this should be around, like, tolerable limit is 60 millivolts per decade, or rather per dB. Okay, so 60 MV per dB. Okay, so this is the tolerable limit. There is an expression for this. I will, recommend that you look it up. Remember this because there was an assignment numerical corresponding to this. So chances are similar questions might appear in your examination as well. DIBL, drain induced barrier lowering. Look at the definition. See what causes it. like what effect it has. The reason I'm writing it over here is it becomes important when we're talking about electrostatics. Now, of course, along with this, we also have the depletion width calculations and things like that. So you can go back and look at the various expressions. So just for reference, I will write it here. So the depletion width will be, what is it? It's square root of, I think, is times the applied potential, surface potential, divided by the total charge. Yes. So that will be Q times MA. So this is going to be your depletion uh, depletion width. So this will also tell us that in the depletion regime, QS is proportional to psi s to the power half. So this is depletion regime, and in the inversion regime, QS is proportional to e to the power psi s. So this is in the inversion regime. In fact, this is also true in the accumulation regime, where instead of applying a negative voltage, I will apply a positive voltage. Or rather than applying a positive voltage, I'll apply a negative voltage if I'm talking about an NMOS. So, accumulation regime. Okay, so this thing needs to be remembered, like these trends. You might have graphical questions where you're asked to find out which is which regime. And from this, we have the body coefficient, which is like the deviation from ideality. So that will be just one second. Let me just look up to make sure I'm not making any further mistakes. Yes. So this is going to be 1 plus CD by Cox. This ratio is important. So ideally, we would want CD to be 0. So ideally, CD has to, or rather, I should say, CD by Cox should be very small. So this implies CD is approximately 0 or Cox is very much greater than CD. These are the two cases. So this brings us to uh, the other important thing in terms of concepts, mitigation strategies. So mitigation strategies. So mitigation strategies, our aim is essentially like when we are talking about mitigation strategies, we just want to bring this body coefficient to as close to 1 as possible, because ultimately both the effects, subthreshold swing and DIBL, are kind of determined or rather dependent very strongly upon this body coefficient. Because, well, DIPL not so much, but subthreshold swing is very strongly dependent on this, because if there is an additional potential drop, like if you remember the model, we have VG and then we have Cox and then we have CD and then we have size. So this is kind of the situation that we have. Ideally speaking, I will want this quantity to be 0, so that I can just directly say the only voltage drop that is occurring occurs across the oxide layer. This is what I would like to say in my transistor, so that I will definitely know what VG I should apply to achieve what VS. Now the presence of CD here kind of disrupts that fact. Like it introduces a variable, this is a variable capacitance in general, a variable capacitance which kind of keeps shifting the value of psi s on VG. Like the controllability of psi s on VG is reduced by the presence of CD. Okay, so I will also write that here with CD greater than 0, VG loses control over psi s. Okay, so when I'm talking about mitigation strategies, again spelled very, very poorly. I apologize for my bad spelling. Here, essentially, what I want is our aim through and through is high, not high, I shouldn't say high, say yes, strong control over psi by Vg. So now the first mitigation strategy, like essentially I wrote everything that is required over here. So either CD should be very small or CX should be COX should be very high. So one, use low doped substrate. Two, use high K dielectrics. So all of these things you don't even have to like remember them as separate points. Just look at this quantity, guess what you have to do to make this one. Okay, so we can do that. What else can we do? You know, this is Cox is some epsilon s a by d. So I can make, to make this very large, I can make d very small. So use thin gates, or like large surface area. In theory, that is also true. However, large surface area of gates would automatically imply long channels, which would imply high DIBM, which is why this is not recommended. Which is why we just talk about thin gates. So this is not recommended. Okay, so these are the different strategies we can adapt to uh, adopt to bring the body coefficient down. Uh, so yes. Now, as we are doing this, we also notice that, say, things like thin gates or uh, stuff like that essentially requires like an overhaul of our fabrication system, as I discussed during, you know, two, was it 2 weeks ago or 3 weeks ago? I think, yeah, it was 2 weeks ago. This was week 11. So that is the takeaway there. Before winding up this section, over here, I will also, yeah, I just wrote that over here. So I'm run out of space. So in general, I will say, remember some things about the Poisson-Boltzmann equation. I did not discuss it in the session because, you know, it doesn't appear in assignment questions, but there may be one or two theory questions. So remember the Poisson-Boltzmann equation, which is ultimately the equation that we use to solve the 2D electrostatics of our like MOS devices. And I will give you one direct effect. So the gate effect and all those things. How does 2D electrostatics influence the system? It is very straightforward. So 2D electrostatics I mean, the takeaway message is exactly what we discussed here. The very first word, I need inversion. So when I apply a gate voltage, my acceptor concentration will get replaced by an effective acceptor concentration. So this will become Na effective. Okay. So every 2D electrostatic effect can be combined into what is called the effective acceptor concentration. So this thing, just look at it in the slides and just remember the theories. There may be one or two questions. Like again, if I were to set a question paper, I would ask questions like this. Yeah, I will put it like that. Although I did not set this question paper. So then we come back to the fact that while we are doing this, let us also explore the added benefits that we might get from using short channel devices. So when we are talking about short channel devices, we discussed two particular instances of them. First is the double gate devices. So when we are talking about double gate devices, more precisely, we actually talked about like in some detail or greater detail, in some detail, we talked about double gate EDSOI, extremely thin silicon on insulator devices. So again, you can see that this already takes care of this thin gate concept over there. So it's a thin layer of silicon on insulator. So essentially, it is going to be acting as a thin gate, and then we are going to have a double gated structure. So most important thing to remember here is double gate implies geometric screening. So geometric screening reduces DIBL. So when we are talking about screening, remember the Debye length. So lambda Debye, or rather let me just call it lambda D. So remember what the Debye length for different devices is. Okay, and so when we are usually considering it's not lambda d, like in the lectures I think it's just LD. So yeah, so this will be given by the expression epsilon as kBd. Again, you ought to remember these things, q squared Na. So yes, this is it. And typically the channel length. So oh no, wait. So this reduces. Then yeah, the second point. So this is the second point. This does not have anything to do with the double gate devices. Sorry if I like even I felt I was implying that. So yeah, I apologize for that. So this is the Debye length. And so if I need short channel, so another way to prevent DIBL is to have short channels. So as a shorthand, you can remember whatever we discussed in 2D electrostatics, it is to reduce subthreshold swing. Whatever we are discussing in these devices, strain engineering and double gate devices, it is to enhance mobility and reduce DIBL. Okay, so short channel devices also have low DIBL, so implies low DIBL, and the criteria for that is lambda min. So this is channel length. Should be equal to, or rather less than equal to, oh no, I'm talking about min. Yes. So equal to LD by 3. So given a particular material, you will know Na and the dielectric constant. So at a given temperature, like operating temperature, you can guess, not guess, you can calculate the debye length. A third of that should tell you what length the channel should have to ensure that there is no like DIBL effects are minimal. Okay, so these are your double gates and short channel systems. Double gates, again, remember that the double gate geometry is something like this. So we have, and you know, so we just have whatever gate material we have, and we have kind of an insulator and silicon on top of that. So essentially, it is like the channel is silicon. So sorry, okay, and this is also silicon. So there are actually two gate voltages that are being applied to this device. So what we will see is that now channel inversion and things like that are no longer an issue here. So if you look at the charge profiles, so for such a device, for a double gate device, so I will write that separately here. So if I'm talking about Q versus psi S for DG EDSOI, then it is going to look something like this. Like the device will have symmetric behavior for both positive and negative gate voltages. So it does not distinguish or discriminate between a positive gate voltage and a negative gate voltage. So this is psi S, this is Q. Sorry, this is yes, Q, and this is psi S. So let me just see this. So the black region, as I've usually followed the convention, is the insulator. So this is insulator. So in such devices, what we are doing is we have like the whole device is surrounded by gates. So that kind of reduces any like that significantly reduces the effect of the gate voltage on the drain source transfer. So the gate voltage kind of the field lines move from here to here. They no longer bend towards either the source or the drain electrons. Okay. And alternatively, if we cannot build double gate or surrounded gate devices like FitFETs, so double, yeah, I should also write multi-gate devices here. In fact, I should have written multi-gate devices over here, but doesn't matter. I will write it here. So in multi-gate devices, so we, again, like briefly, you would have seen things like FitFETs, where the gate is kind of like a fin over the channel. So it is surrounding the channel. So similar effects also take place over there. Okay. So that's that. And finally, uh, we have strain engineered devices. So we have strain engineered devices. So now these are again, this is done relatively recently, so I'm not going to go into too much details. So we can have two kinds of strain. We can have tensile or compressive strain. Strain. What does strain do? Strain reduces effective mass, so this implies higher mobility. And strain also implies we have different subbands forming the material. Because strain, okay, I should write this properly. And again, there was a typo there. Strain first implies confinement, first and foremost. Okay, and that further implies subband formation. So this is the more generalized approach. And when we have subband formation, one of the effects is we have, as a consequence, low intervally scattering. Okay, so these are things. And when we are talking about subbands, remember that we have primed slash unprimed energy ladders. And what else is important here? I mean, there's plenty of things that are important. Oh, yes. So remember 1 upon m star average is 2 upon m star longitudinal plus 4 upon m star transverse. So this is for tensile strain. Also remember things like isoenergy. So here the concepts that other things that we looked at are isoenergy surfaces, and in a way we also looked at subbands. Okay, so by and large, these are the things that you will have to remember in such devices. So when we are talking about strain engineering, these are the things that happen. Also remember that strain engineering is done by forming heterojunctions. More precisely, we form like junctions between, so examples, we have Si, SiG, silicon germanium. So usually the lattice constant here is larger, it is smaller, so it introduces strain in the silicon. So again, there are expressions for the lattice constant. This was an assignment question. Go back, look it up. And the second last topic that we are looking at, again, I'm going to be very, very brief here. First thing to remember, these are 0D systems. It looks like OD. I will write this so that there is no confusion. Zero-dimensional systems, or rather zero-dimensional channels. Okay, so G0D of E is sigma over I delta Gi, which is the degeneracy, delta E minus Ei. So how many ever energy levels are there? Just sum over them. So zero-dimensional channel. So this automatically implies only discrete energy levels. Like there is no continuum at all. levels, and there is this over here. Gi is the degeneracy. Okay, and one more thing that needs to be remembered is, so if I talk about quantities like ionization potential, so this is essentially E highest occupied. So E highest occupied minus E vacuum divided by Q. So this is the ionization potential. Why did I write it as potential? I think my brain has stopped functioning at some level, or I'm probably more eager for this course to end than all of you, which is kind of sad. And then we have what is called the we have the Fermi energy. So Fermi energy is energy required to introduce one more electron to the system. So it is not the same as E highest occupied. I mean, may not always be the same as the highest occupied energy level. Okay, so this is the energy required to introduce one more electron, and there is also the concept of quantum capacitance, where we know that like Q is delta Q is C times delta V, and we just multiply by delta V on both sides, so that will give us delta E is, so essentially C is proportional to delta E divided by wait a second. Yes, I made the same mistake. So this is delta N squared delta E. Yeah. Where did I put brackets? So typically, like I did a numerical for this, so just check the last week's video. You take the system, you see how much additional energy was spent in introducing new electrons into the system, divided by the total charge. That will give you the average energy spent per, or sorry, calculate the average energy per electron divided by charge to get the quantum capacitance. So this is C quantum. So that will always be proportional to something like this. Okay, so this is more or less what is required for quantum dot devices in this course. Finally, we come down to thermoelectric effects. So again, starting point is our good old current expression, integral T of E, M of E, F2 minus F1. So in this, again, I'm not going to go through any derivations. Two effects are covered in detail, Seebeck and Peltier. So what should we remember for Seebeck? Seebeck tells us open circuit voltage as a result of temperature difference. Okay, so I'm not even like going to write the expressions here since I just did it in the last week's slides. Just go there and see that. Peltier effect is kind of the opposite. It is temperature difference my God, my brain has stopped working. Difference as a result of current flow. Just remember these two things. So if a current is flowing from the source to drain, they will be at two different temperatures. Now, if electrons are moving from, so you can intuitively guess it. If electrons are moving from source to drain, it implies a higher energy electron is moving, like always, particles will move from a high energy state to a low energy state. So higher energy electron is losing energy and going to a low energy state. So there is an energy loss that has occurred when the electron moves from point, like the first electrode to the second electrode. Now, this energy loss is typically considered as the like that is, yes. So there is also a third effect which is called the Joule effect. This is energy loss as the electron move from source to drain. Okay, so I'll just write it from source to drain. Okay, so now that is the Joule effect. So which is why when current flows through a wire, the wire starts heating up because it is radiating energy. Peltier effect, on the other hand, tells us that a temperature difference actually forms between the two ends of the wires. So temperature difference between source and drain. So now why does this happen? It is actually quite straightforward because as temperature increases, the occupancy of electrons near the Fermi level kind of keeps, like the occupancy probability keeps coming down. And as temperature decreases, the probability starts going up, which implies the electrode that is supplying the electrons, effectively the temperature is going up because the occupancy probability is coming down because more and more electrons are leaving that place. Like essentially, I have an electron that is from here traveling through the channel and going here. So it is jumping from here to here. Now, as it is doing that, over here, effectively, T is increasing. Whereas here, effectively, temperature is going down. Opposite happens for holes, because if there was a hole that went from here to here, which implies an electron came into this and an electron left this. Okay, so effectively the temperature goes up here, effectively the temperature comes down here. This temperature difference is the Peltier effect, whereas Joule effect is the heating of the channel itself. Okay, so these are the three thermoelectric effects that are pertinent to our discussions. And with that, I come to the end of the formal part of this session. I would like to give you some, although this is like the last minute, but of course, yeah, this is last minute advice. So I will just write it as last minute tips, both in my video and the course. So first and foremost, revise the assignments. So they are essentially the blueprints for your exam questions. Go through the quiz questions, uh, look at the solutions. If you have any doubts, please post them on the forum. I will still be looking at them till the day of the examination. So revise assignments, understand those questions as thoroughly as possible. Any doubts you might have, please ask on the forums. I will be more than happy to answer them. Second, I have given more or less like these are almost 20 slides worth of material here. Revise the concepts. I mean, the assignments itself will contain most of them, but otherwise also revise the concepts. So, and after that, practice some numericals. So, practice problems, you can, redo the problems that I did in the session. Some numericals are also kind of calculated during the lectures, and you can, there are some textbooks that are referred to in the slides. You can also, if you can find them, you can work out the numericals there. The reason I'm putting this third is, as I mentioned before, the conceptual questions will be more uh, like the probability of having conceptual questions is definitely higher than having numericals. So revise the assignments, do this and do this. Things should go more or less smoothly for your examination. So with that, I am formally concluding these discussion sessions for the St. Peter course, and I wish you all the very best with your examinations and any and all future endeavors. Thank you all for listening, and goodbye.